Alright guys, okay, so we are going to work on polygons and how the diagonals in a polygon help us find different things that are going to be useful later, okay? The first thing we need to understand is that a polygon, it's not in 3D, right? A polygon, it's in 2D, that means 2 dimensions. So I actually do have some definitions over here. Hopefully you're gonna be able to see it. A polygon is a 2-dimensional figure bounded by straight lines forming angles between each other, all right? I just figured it was a little bit faster if I had it written down already, and so the video can be shorter and not so complicated to upload later. So what we need to understand there is that any type of polygon, it's always gonna be formed by straight lines. So if you have something like this, that is a polygon, right? It is a polygon. Why is it a polygon? Because it's a plane figure, a 2-dimensional figure that is bounded. Bounded means the borders are made of straight lines, right? Now, this is one type of a polygon, but then this, it's another type of a polygon, right? Now, you gotta keep in mind that both are polygons. If you think about it, because of the definition of polygon, they both are 2-dimensional figures. They both are made by straight lines, and they all form angles between the lines that form them, right? So what we need to keep in mind is that they both are polygons. Now what happens here is we actually have 2 kinds of polygons. We have convex polygons and we have concave polygons. They also are right here, so you can check on those definitions over here. A convex polygon, it's a polygon where no diagonals goes outside the shape, or a concave polygon is where the polygon where at least one diagonal goes outside of the shape. So in that order of ideas, we need to understand what a diagonal is first, right? Well, a diagonal is pretty much a line segment that is going to link, that means to connect, right? 2 vertices that are next to each other. So in this case, I don't have any more colors, guys, sorry, of markers, but I'm gonna try to make it as clear for you as I can with only the 2 colors I have available right now. But then what that tries to tell us is that a diagonal goes from one vertex and connects with another vertex that is not next to the vertex we started with, right? So this vertex over here is going to be able to actually make what? One more diagonal over here, sorry, right? And then it's also going to be able to make another diagonal over here. Why? Because these 3 vertices are actually not next to this vertex. Think about these 2 vertices. These 2 vertices are next to this vertex over here. So what that means is that a diagonal cannot go from this vertex to this vertex over here, or from this vertex to this vertex over here. We cannot do that. That's why from this vertex only we can make 3 diagonals. So again, a diagonal gotta be a line segment that connects 2 vertices that are not next to each other. In that order of ideas, if we go and work with this polygon we had over here, which by the number of sides I could actually say, let me count, 1, 2, 3, 4, 5, 6, 7, 8. It's actually an octagon. It's just, it is irregular, right? But it is an octagon. if I think about it, this vertex over here, I know the vertex next to that is this one over here and this one over here. So that means I can actually do a diagonal like this going to that vertex. I can also do a diagonal like this. I can also do a diagonal like this. I can go to this one over here, or I can go to this one over here, right? So I am able to get 1, 2, 3, 4, 5 diagonals out of this one vertex, right? So what that means is that I never use the vertices that are next to the vertex I had at the beginning. Now, what is the difference between these two polygons? Well, this polygon over here is what we are gonna call a concave polygon. Why is it a concave polygon? If you can notice, there are two diagonals here that in order to be able to go from one vertex to another, they gotta go outside of the polygon somehow, right? So we call it a concave polygon. Hopefully you're taking notes, because once we come back to school, all those notes are gonna be useful. We're not gonna have YouTube at school, you know that. So that's gonna be the concave polygon. So this one over here, if we actually were able to go from each one of the vertices in this hexagon, we know not even one diagonal is actually gonna go outside of the hexagon, right? So that's why we know this is gonna be a convex polygon. Guys, in math, everything we do in math, or with like the basics of geometry, and every single time we talk about regular polygons, and of course all the formulas we work with in geometry that you are gonna know about later on during this class are actually based on convex polygons, not on concave polygons, all right? So I know we've seen irregular polygons a lot of times, and we're actually able to classify them by their number of sides. But everything we're gonna do in lesson 1, it's related to convex polygons. Otherwise, the formulas we're gonna build a lot of times are not gonna work out, all right? So we need to think about regular polygons all the time, all right? Regular meaning polygons with the length of their sides that they equal to be equal all the time, right? Okay. Saying this, let's just go ahead and start working with what is important for us in the lesson, and that is, how do we talk about the diagonals in a polygon? I mean, the diagonals in a polygon later on are going to help us figuring out a lot of things for the angle sum of a polygon, or the measure of one angle in a polygon, right? So this is how this works. Think about this. I want you to think about that. We're going to have a triangle here. Hopefully it kind of looks like an equilateral triangle. Not sure about that though, right? That please make on your notebook. That's not a straight line. Well, not at least for me. Please make on your notebook a square. Hopefully this looks like a square. Maybe not the most perfect square, but it's okay, I guess, right? So this triangle is going to be the representation of all triangles, and then this square is going to be the representation of quadrilaterals, right? Convex quadrilaterals, right? And then we are going to talk about a pentagon, which is a little bit harder to do, and if we were at school, I would probably teach you how to do it with a compass, right? Because it's the only way to actually make a perfect pentagon. And then we're gonna have a We're gonna have a hexagon, and then I'm gonna do an octagon, which, yeah, probably just those, because I need space. And as you can tell, my board is not teacher size. It's actually where my sisters write down little notes for everybody and stuff. So I've been stealing our home's board. Okay, well, pretend this is a perfect octagon, please. I know it's not the prettiest. I can actually make it a little bit better, you know. Let's see. This is probably gonna work a little bit better. Anyways, well, probably you're working at home. At the same time, I am working here. That'd be great, because then at the end of the class, your notes are gonna be taken and you're gonna be fine. You don't have to spend any more time besides just watching the video and taking notes at the same time. That would be great, because then you're gonna be just ready to write down your questions at the end of the session. All right, so we have those 5 polygons, okay? Tell me. Well, you cannot tell me, but I'm gonna pretend you can tell me, because I really wish we could have done this lesson together. This is pretty interesting. We're gonna build stuff in math that not a lot of people can actually do it, not even when they are older, like, you know, 10, 11th grade. They're not able actually to do this. So let's think about this. Can we actually draw any diagonal in the triangle? I mean, let's think about this vertex over here. I need to go from this vertex to a vertex that is not next to that. And if I look at it, I only have 2 more vertices I can use, but they both are next to this vertex. So here, we actually cannot have any diagonals. That's a 0, by the way. All right, we actually have 0 diagonals here. All right, now think about the square. If I think about this vertex over here, yes, these 2 vertices are next to it, but this one is not. So I can actually build a diagonal that way. And if I go to this vertex over here, then I can just draw this opposite over here, right? If I go to the other 2 vertices, I'm gonna end up having the same diagonals. So I'm not gonna repeat diagonals. And so I know here I have 2 diagonals. Now if I go to the pentagon, I can start with this vertex over here, and I know I cannot use any of these, but I can definitely go and draw these 2, right? And if I use this one over here, I cannot use these 2, but I can definitely use these 2. So here's 1, and here's 2, another 1. It's another 1. Then if I go here, this one it's already used. I cannot use any of these, I'm sorry. But I can definitely go to this one and to this one. I already have one here. I'm not gonna do another one, but then I'm gonna draw. Oopsie. I'm gonna draw another one over here. Hopefully you're able to see all this. And if I go here, the only 2 I can make are already drawn. So I'm pretty much done with it, right? So if I think about it, let's see. I have 1 here, 2 here, right? Then I have 3 here, 4 here, and then this one is already counted, but this one is not. And then the other ones are pretty much what we already drew, right? It's the same thing. So think about that, and then if my calculation is not wrong, then I should be able to actually have the amount of I forget, the amount of diagonals, which is 5, right? So 5 diagonals right here is what we're gonna have. 3, there we go. And if I keep going here, then let's see, I have over here 1, and then I have 2, and then I have 3, right? And then I have 1, 2, 3, that's 6. Over here I already have 1, so I'm only gonna have to make another 2, so that is 8. I already have 2 here, so I have only 1 left, which is right here, so that's 9. And I got 3 here, I got 3 here already. So I'm having here 9 diagonals, right? And this is probably the longest, right? So because I gotta go 1, 2, 3, 4, 5, right? 5. And then if I go here, there is gonna be another 5. So 1, 2, 3, 4, 5. And here I should have 5, but I already got 1. So I'm gonna just draw 4. So I had 10 and 4, 14. Right? Now I have 2 here, so that means I have 3 left to draw. And I have 14, so that means 17 now. So 1, 2, I gotta go 1, 2, and 3. And if you look at here, I also have 3 left to draw at 17 at the beginning, so that is 3 more, so that is 20. And it's 1 for here, then 1 for here, then 1 for here. Hopefully, while you're doing it at home, you're gonna be able to see it better, because I'm not sure how clear is it from here. And then I have 1, 2, 3, 4 here, so that means I only have 1 left, which is this one over here. So that would be 21 diagonals, because if you count on this 2, I have 5 already. So I have 21 diagonals. Okay? Now if you think about it, I do know I have 3 sides here. I have 4 sides here. I have 5 sides here. I have 6 sides. I'm gonna write it down here. Yeah, and I have 8 sides down here. If you look at it, I'm getting 4 sides, but out of each vertex, there's only one diagonal coming out. So that is 3 less than the amount of sides I have. Think about the Pentagon. The Pentagon, I am able to actually get 2 diagonals out of each vertex. That means is 3 less than the amount of sides the Pentagon has, which is 5. Now think about the hexagon. The hexagon allows me to get 3 diagonals out of each vertex. So that is 3 less than the amount of sides in the hexagon. And if I think about the octagon, I'm able to actually get 5 diagonals out of each one of the vertices we have. So that again is going to be 3 less than the amount of sides. That gotta tell us something, right? We've been talking about patterns, and so those patterns we can tell here are gonna tell us something. And my question for you guys is, and if you want to pause the video and think about it before I say anything, you're more than welcome to, because remember, I love when you guys are just trying to build stuff yourselves. So you can just pause the video and think about this. How can I build a formula, a mathematical formula, to get the amount of diagonals in each one of the polygons? How can I do that? How is that possible? Well, if you are already back and you depause the video and you want to know if your answer is actually what I'm about to say, it's time. Think about this. I'm actually needing the space. Okay, let's think about this space over here. So I have n, right? N, I'm going to define it as amount of sides of a polygon, okay? Of course, I'm gonna call D a diagonal. Actually, the amount of diagonals. Remember, we always gotta define the variables. If we don't define the variables, we are not gonna be able to express our thoughts clearly, all right? Well, think about this. We know subtracting 3 gotta be somewhere, right? It gotta be somewhere. Now, think about how if I take the amount of sides and I subtract 3 from it, I'm gonna get the amount of diagonals, right? But then I also need to understand that the amount of diagonals I'm getting is a vertex. It's only coming out of a vertex, but I need to count all the vertices we have in the polygon, which we know is the same number as sides the polygon has, right? So whatever amount of diagonals that come out of one vertex gotta be the same amount for all vertices in the polygon. But then, if you think about it, I need to get to the number of diagonals I got here somehow, right? So that's how remember when we said we need to adjust the pattern when we were working in chapter 13? That's what we do. We are using 2 facts that are very clear for us, and that is how to get the amount of diagonals per vertex in each polygon, because it's just subtracting 3 from the amount of sides the polygon has. But then I know I gotta keep in mind all the vertices in the polygon, which is the same amount as sides the polygon has. And that order of ideas, what we need to understand is how am I going to get the formula. So I'm gonna erase the triangle right here for a minute. I'm going to erase that so I have a little bit of space. And let's think about this. If I had n minus 3, which is the amount of diagonals I get out of one vertex, and then I multiply that by the amount of vertices I have. For the case of the square, that would be what? 4 minus 3 is 1, right? So I could say 4 minus 3 is 1. And then I know the amount of vertices is the same amount of sides, so that's another 4. So I know I have 4 times 1, which is 4. But I need to get 2, so we need to adjust that pattern. So that means that I am going to divide it by 2. And let's see if that works. Well, of course it's gonna work, right? But let's see if it works for everybody, because we need to make sure it works for everybody, remember? So this is what we do. Now we're gonna try it for the pentagon. The pentagon is, we know it's gonna be 5 minus 3, so we get the 2 diagonals. Then we multiply it by 5, because we have 5 vertices in the polygon, and we're gonna divide it by 2. Does this give us 5 diagonals? Let's see. Well, 5 times 2 divided in 2, you cancel them out and you get 5. So great job. We actually know it's gonna work out. You can try for for a hexagon and for an octagon, and you are gonna notice that it actually is true. This is the formula we need to work with, okay? The diagonals, the amount of diagonals in a polygon is gonna be found by this formula. I can actually write it down this way if you feel it's a little bit more clear. Right? And so that way we're able to actually find the diagonals. So if in the goal test I ask you how many diagonals does a nonagon have? A nonagon is a polygon with 9 sides. It's pretty easy to find out with this formula, right? So this formula is going to be very important for us once we take the goal test. Please keep it in mind. And at some point, you need to know it by heart, all right? Okay, now that is one part of the lesson. How do we figure out how many diagonals a polygon can have? But now let's think about how would that help us to find out the angle sum of a polygon, whatever kind it is, because depending on the amount of sides, we know we can have different types of polygons. Now remember, we're talking about convex polygons all the time. So think about this. In the book, they said, how about you cut the polygon using the diagonals and then you count the amount of triangles. Then that amount of triangles you multiply by 180, and then that's going to allow you to get the angle sum, correct? Is that it? Is that true or not? Yes, it is, right? So think about this. If we want to think about, again, the angle sum, well, we know a triangle. A triangle has an angle sum of 180, right? Remember? If this is angle B, angle A, B, and C, we know angle A, B, and C are going to be the sum of all the angles is going to be 180 degrees. We know that. But how do we work it out for every single type of a polygon? How can we make it clear for everybody? Now, of course, we need to understand how are we going to get the triangles, right? So let's come back to the figures we had. And then again, let's think about the triangle. Let's talk about the square, and let's talk about the pentagon. I'm going to just work with these three just because I really don't have any more space. But you can try with more polygons if you want to, it's fine. Okay? So think about this. How can we divide, using diagonals, how can we divide the polygon into triangles? So, again, can I have diagonals here? No. If I cannot have diagonals here, well, that means that the only triangle I'm going to get is the triangle itself. So here, I'm only getting one triangle. I'm gonna say, in this case, one inner triangle is going to be the same as the triangle itself, right? Just because we cannot do or draw any diagonals. Now think about the square. If I make one diagonal here, then I'm going to be able to get two triangles. Would that make sense to get the other one diagonal working this way down? Well, not really, because we already have triangles. We don't need to have smaller triangles. That's not the point. The point is just to have triangles in the polygon. So with one diagonal is enough. So one diagonal gets me what? Two inner triangles. Inner means inside, right? Okay. Now think about this. Well, you had it in your book, I believe, right? Maybe I should do. Well, okay. I think you have this in your book. So I can, out of one vertex, remember, we can make two diagonals because that's what we got from the exercise we did before. And that is, in a pentagon, each vertex gotta get the amount of sides minus 3 amount of diagonals. So I know I can get two diagonals here, and then I'm gonna have 1 and 2. I'm gonna have here 1, 2, and 3 triangles. And again, I don't really need to keep on getting smaller triangles. Sorry, inner triangles is what I meant. 3 inner triangles, right? And again, what we are gonna think about is the amount of sides each side has. And so here we have 3 sides, here we have 4 sides, and here we have 5 sides, right? I'm gonna do the hexagon very quickly, and maybe I can just use a little bit more space over here. Sorry guys, I didn't know my sister's camera has a limited time for recording, so it just turned up, and I'm gonna have to send you 2 videos then instead of 1, but I guess it's fine. So we were at the point where I was about to draw this polygon, right? Which is the hexagon, and as we talked about before, we can actually make 3 diagonals out of this vertex, just because we figured it out because of the formula, right? We can get the amount of sides minus 3 amount of diagonals from each vertex, and then all this formula is going to be for the total amount of diagonals in a polygon. So we got here this triangle, but then we can actually have 4 triangles. And again, we're not going to try to make any smaller triangles. So we know we have 4 inner triangles. 4 inner triangles, and we know we have 6 sides. Now, how does it tell us? We're not going to erase this part because I don't want to erase it really. But let's think about how can we actually find a pattern again to get the angle sum of a polygon. We already know it's a matter of knowing the amount of inner triangles we can get times 180, right? So if we know we have 3 sides and only 1 inner triangle, and then 4 sides and 2, and then 5 sides and 3 inner triangles, and 6 sides and 4 inner triangles. Now we can actually tell that the amount of inner triangles are going to become, we're going to be able to get it, we're going to be able to get it if we take the amount of sides and subtract 2 from it, right? So now we are going to have n as the amount of sides. Always remember, once we give a name to a variable, we stick with it. So n is going to stay as amount of sides. That's not going to change. Okay? And so n minus 2 though, it's going to be the amount of inner triangles we can actually get in each case. And then the only thing we need to do now is to multiply by 180, just as the book says. And that is going to give us the angle sum. I'm going to call it AS, all right? Angle sum is going to be equal to n minus 2 times 180. What do I need to know though? The amount of sides the polygon I'm working with has. If I have that, then I'm able to find the angle sum this quick, and I don't have to draw. What I want you guys to understand is I'm teaching you how to get the formula so you don't have to spend your entire life drawing diagonals and triangles, inner triangles in a polygon to find out the angle sum. It's just a matter of using that formula. Now, I believe the formula now is a little bit clearer since yesterday you were reading the lesson and you were working on your own trying to figure it out, and you probably draw a lot. You probably did a lot of mental math too. But this way, we're going to be able to get the answers within seconds. So my advice, please make a little flashcard about these 2 things. I'm going to give you a third one in a minute, so you actually are able to learn them by heart. This is going to save you a lot of time in goal tests, all right? Okay, so now let's think about the third question that the lesson says, and that is, how do I get the measure of one angle? How do I get the measure of one angle in a polygon? Whatever the polygon is, if they give me a polygon, a convex polygon, if they give me a polygon, and I need to know what is the measure of one angle in this, or what should be the measure of one angle in that polygon. Remember, in this case, we would have to talk about regular polygons all the time, because then talking about irregular polygons would make it really complicated. So right now we're talking about regular polygons. Now the angle sum though is going to work for any kind of polygons, whether it's convex or concave. We would have to actually make sure all the addition of all inner angles are gonna get to the angle somehow. But to actually get the angle measure of sorry for the redundancy, but of only one angle in a polygon, then we need to think about only regular polygons. There would be no other way actually. So how do I get it? Well, it's pretty easy. Just think about this formula we just got here. The only thing we need to understand here or to work with is the measure of an angle. It's gonna be pretty easy to find because we need to just work with the initial formula to get the angle sum of the polygon, but then we're just gonna divide into the amount of sides the polygon has. If we do that, then we're gonna be able to find the measure of only one angle, right? It's that easy. Remembering that n is always gonna mean the amount of sides of a polygon. Now, I'm gonna look at some of the exercises they had, and probably you did a lot of mental math to find it out, but for instance, number 3, which kind of looks a little bit really big, right? And none again, remember, none again means 9. None again means 9 sides. We have a polygon with 9 sides. So in this case, n should be 9. If I ask you guys, okay, can you please find the amount of diagonals? Can you please just find the amount of diagonals in a nonagon? Well, I'm just gonna go ahead and use this formula over here, right? So I'm gonna say, you know what, 9 times 9 minus 3 over 2. That is gonna get me, of course, 9 times 6 divided into, I like to cancel things out, so that is gonna be 27. So I know I have 27 diagonals here. How much time did I take? Probably 15 seconds. It could be less if I'm fast enough, right? Now, let's think about the angle sum. The angle sum here is going to be, again, 9 minus 2 times 180. That's going to be 7 times 180. And 7 times 180, that would be 700 times 560. So that would be 1,260 degrees. So we're having 260 degrees, right? How much did I take? Probably 10 seconds? Yeah. Now the measure of an angle. Well, I already have this. So I do know the only thing I have to do is to take the angle sum and divide it into 9. So let's do that. I'm just gonna do it over here very quickly. Right? And so that's going to be 1 time, then this is going to be 4, and so that is going to be 140. So I know each angle in a nonagon, in a regular nonagon, is going to measure 140 degrees. Well, that's pretty much it, guys. That's what you actually had to think about. That was the only thing you guys had to work on. I really hope this is helpful. Again, what I want you to understand is that sometimes people think this stuff is really complicated, but it's not. It really is a lot of times a matter of understanding the meaning. If you understand the meaning of the formula just because we built it together, then using it is not going to be a problem, all right? Please feel free to write down your questions on your notebook. We will talk about those questions later on. And go ahead and finish the lesson if you feel free to do so. All right? Okay then, well, I'll see you later. Any question you have, I'm here for you guys. All right then, see you later.